Hello everyone! In this video, I'll show you the solutions to the algebraic manipulation and factorization homework problems. So if you haven't already watched the class 2 video, please make sure to go do so, as many of the techniques and factorizations were covered in that class that we will be using today. Also, I encourage you all to try these problems before watching the solutions to them. Let's begin with the first problem. Two non-zero real numbers, a and b, satisfy AB is a minus b. Find a possible value a divided by b plus b divided by a minus ab. So whenever you have fractions, you always want to try to find a common denominator. So you can rewrite this as a times a over b times a plus b times b over a times b, which is, well, both denominators are ab, so it's a squared plus b squared over ab. And we'll worry about this fractional term later. This fractional term, we'll subtract it at the end. Right now, I'm only dealing with the two fractions here. So the AB term will subtract at the end. And how can we find the value of this? Well, we have AB terms, so we somehow want to cancel terms here. So we want to cancel the AB term with something. Similarly, we also want to somehow use this fact that we haven't used this fact yet. So somehow we want to use this fact. So what we can do is we somehow want to represent our terms in terms of a minus b. Because then if you do a minus b, then some terms will cancel. To explain what I mean in more detail, let's just rewrite this as a minus b squared plus 2ab. So this is just equal to a squared minus 2ab plus b squared. So when we add 2ab to it, the negative 2ab terms goes away. And then we divide that by ab. And this simplifies to a minus b is just ab. So ab plus ab squared plus 2ab divided by ab is equal to ab plus 2. Because now what? Well, now what we can do is we can subtract ab. So we can do minus ab, because remember we have to do minus ab, we were leaving that till the end, and we get 2 as the answer. So to summarize, the key steps was to rewrite the fractions in terms of an equation, and then make our substitution. And then we get some terms canceled out really nicely. Okay, so for the next problem, this is a trick that we covered in the class, remember? So for this, what we have to do is to square our expressions in order to get terms that we want. So firstly, let's do x plus 1 over x squared. If you do this, we get x squared plus x times 1 over x plus 1 over x times x plus 1 over x squared. Okay, and now what? Well, these two terms are both 1 and 1, so overall, they're 2. So overall, we have that x plus 1 over x squared. Well, we know x plus 1 over x is 4, so we have 4 squared equals x, or 16, I'll say, plus squared plus 1 over x squared plus 2 is 16, meaning that we can subtract 2 from both sides to get x squared plus 1 over x squared is just 14. And now we can square it again. So we do x squared over x squared squared to get x to the 4th plus 1 over x squared times x squared plus x squared times 1 over x squared plus 1 over x to the 4th. And then these terms are both 1. So we have x to the 4th plus 1 over x to the 4th plus 2, because we have two terms that are both 1, is x squared plus 1 over x squared. So this is equal to 14 squared. Because x squared we found is equal to 14 in the previous expression. So now we know that 14 squared, or 196, is equal to this quantity, meaning that x to the 4th plus 1 over x to the 4th is just 194. Now what? Well, now let's square the expression again. Because when you square it again, now we'll get those x to the 8th and x to the 1 over x to the 8th terms. So let's square it. X to the 4th plus 1 over x to the 4th squared. And I'm not going to do it again. So x to the 8th plus, I'm just going to read directly right now, x to the 4th times 1 over x to the 4th plus 1 over x to the 8th. And x to the 4th plus 1 over x to the 4th is just 194 squared is equal to x to the 8th plus 1 over x to the 8th plus 2. And 194 squared is just, 194 squared is 37636, I think. Okay, so 194 squared should be 637636. Is equal to x to the 8th plus 1 over x to the 8th plus 2. And then we can subtract 2 from both sides to get 37634 is x to the 8th plus 1 over 8 x to the 8th. And if you're curious how I actually did 194 squared, Arthur Benjamin actually made a trick where basically 194 squared, so basically we have, this was Arthur Benjamin's trick, that 194 squared minus 6 squared is equal to 194 minus 6 times 194 plus 6. And we can see that 194 squared will then just be equal to 188 times 200 plus 6 squared. And that's how, and that this is just 37600 plus 36, which is 37636. So that if you're curious how I did 194 squared, is I actually use this trick here. Because this is like a clever, another factorization you can think of it as. Except now we're using a factorization with different, now we're using a factorization to help us calculate 194 squared very quickly in our head. This is a cool mental math trick created by Arthur Benjamin. And then from here we can see that our answer is just 37634. Okay, so now let's take a look at our next problem. This one. So this one has some number theory involved as well. Let a and b be relatively prime, a is greater than b is greater than 0, and we have that this big expression is true and we want to find a minus b. How can we do that? Well, we see a minus b and some a minus b terms, so let's try to factor that out, see what that gives us. We can factor out in the beginning, well, okay, how about let's make that more clear. So we can see that it's a cubed minus b cubed, and by difference of cubes, that's just equal to a minus b times a squared plus ab plus b squared, right? Divided by a minus b times a minus b squared. Because I'm just expanding this x minus 2. And as you can see here, since a is greater than b, that means that a minus b will not be 0. Because a is greater than b, so a minus b will be positive. And if it's positive, then we can just cancel it out. And this simplifies to a squared plus ab plus b squared divided by a squared minus 2ab plus b squared. Which is equal to, well, from here, what we can do is you can say this is equal to, well, I'm going to group the a squared plus b squared terms together, minus plus ab, and I'm going to group the a squared plus b squared terms in the denominator too. And this equals 73 over 3, right? We're given in the problem. Okay, so now what? Well, again, we have a squared plus b squared, and we want to find a minus b. So we can represent a squared plus b squared in terms of a minus b. It's going to be a minus b squared plus 2ab plus ab divided by a minus b squared plus 2ab, because a minus b squared, remember a minus b squared plus 2ab is just a squared plus b squared, so this quantity. Same thing in the denominator. So I'm rewriting it in this way. Okay, and now we just simplify this out is equal to 73 over 3. Oops. And this is equal to a minus b squared plus 3ab over a squared minus a minus b squared, because the 2ab's cancel out. And this is 73 over 3. Because now we just have to solve this equation. So now, let me just copy this really quickly and paste it here. So this is equal to 73 over 3. And then we can cross multiply on both sides to get 3 times a minus b squared plus 9ab is 73 times a minus b squared. And now what we can do is we can say that 9ab is just 70 times a minus b squared. Okay, so now what? Well, now we know that this side is a multiple. Oh, let me use a different color just to make it a little bit more clear. So this side is a multiple of 9 because it's 9 times a times b, and a and b are both integers. So the left side is a multiple of 9, meaning that the right side also has to be a multiple of 9. So that means that since 70 does not have any factors of 9, so 70 is not a multiple of 9, and since the whole right-hand side is a multiple of 9, a minus b squared has to be a multiple of 9. Because 70 is not a multiple of 9, and a minus b squared will have to be a multiple of 9 in order for the right-hand side to actually be a multiple of 9. So that means a minus b squared has to be a multiple of 9. Similarly, we also have that since this right-hand side is divisible by 70, this left-hand side also has to be a multiple of 70. And since 9 has no factors of 70 in it, AB will have to be a multiple of 70. So now we know that AB will have to be a multiple of 70. And a minus b squared will have to be a multiple of 9. Okay, so now we have these two quantities here. What we can do is you can see that, okay, we know that a and b are relatively prime from the problem. Remember, a and b be relatively prime integers. So if a and b are relatively prime, then we also know that so we know that a and a minus b will be relatively prime. So by the Euclidean, we'll actually explore more about these kinds of things in the number theory class. So make sure to stick for that class or watch the video for that class. By the Euclidean algorithm, we have the GCD of a comma b is just equal to GCD of a comma a minus b. And we know the GCD of this is 1, so the GCD of this will also be 1. So now we know that a and a minus b are relatively prime. And similarly, we have the GCD ab is 1, meaning that GCD of b minus a and b will be relatively prime too, or a minus b and b will be relatively prime, I should say. So we also know that a minus b and b will have GCD of 1. Okay, so now we know that if these two things have GCDs of each of these quantities respectively, then what can we do? Well, then we see that if a minus b is relatively prime to a and a minus b is relatively prime to b, a minus b will be relatively prime to a times b. So this will be relatively prime to a times b. Okay, so what does that mean really? And that means that a minus b squared will have to be equal to 9, and ab will have to be equal to 70. Because remember, we found in the beginning that a minus b squared is a multiple of 9, and ab is a multiple of 70. And if this was like, let's say 18, for example, so if we made this 18, then this would also have to be 140 in order for the quantities to be equal. But then that would mean these two quantities share a prime factor. But we found that by the Euclidean algorithm, these two things can't share a factor because we know a and b are relatively prime. And by the Euclidean algorithm, these two things, these red expressions I underlined will also have to be relatively prime. So we see that has to actually be 70, that has to be 9. And now we can really solve that a minus b is just 3. Because we know they're both positive. And we know a is greater than b. So a minus b will be positive. So a minus b is 3 from here. And that's the solution for this problem. And don't worry, if you understand the Euclidean algorithm that I used, we'll actually talk more about the number theory class. Okay, now let's take a look at the next problem. This one is a clever application. So for this problem, what we do is you see a minus 1 over a squared is 4. We want to find the absolute value of this quantity. So what we can do here is you can say that a minus 1 over a is just going to be plus or minus the square root of 4, or plus or minus 2. So that's something we can immediately see from this equation. That might be useful. Maybe it will. Who knows? And then we can also see that a minus 1 over a squared is a squared minus 2 plus 1 over a squared. And this is equal to 16. So this is equal to 4. 4 is equal to 4. Meaning that a squared plus 1 over a squared is 6. Interesting. So that gives a lot of information here. But rather than just directly solving for a in a brute force manner, how can we use that in our problem here to find a cubed minus 1 over a cubed? Well, remember difference of cubes? We learned from the class that difference of cubes, we can write it in this way. right? So what we see here is that, we can just rewrite this as x minus y. Well, what is x minus y? X minus y. Well, so by difference of cubes here, we can just rewrite this as x cubed minus 1 over x cubed. So this is difference of cubes. And I'm going to apply difference of cubes to our expression here. A cubed minus 1 over x cubed. So let me write a instead. So in order to find a cubed plus 1 over a cubed, let's just say that, make the substitution, x is a and y is 1 over a. So then I can use difference of cubes to get that this will just be equal to a minus 1 over a times a squared plus 1 over a times a plus 1 over a squared. And a times minus 1 over a is just plus or minus 2, right? And we'll see later it won't matter whether it's plus 2 or minus 2. So I'll just say plus or minus 2. And this quantity is just, well, this is just 1. And you found earlier that a squared plus 1 over a squared is 6. So this will just be 6 plus 1, right? Because 1 over a times a is 1. And a squared plus 1 over a squared we found to be 6. So this is just going to be equal to plus or minus 2 times 7, which is plus or minus 14. But then we want to find the absolute value. So we know it just has to be 14, because we want to find the absolute value anyways. So 14 is the answer. And that's it for this problem. And this problem was really smart, in my opinion. It came from Math Counts Nationals. So the idea was that we can use difference of cubes. So that's how I thought of expanding some difference of cubes and then using our information to plug in the values into difference of cubes. So whenever you see these kinds of different like squares and you're subtracting them, cubes, you're subtracting them, cubes, you're adding them, these kinds of things, you always want to tend to think of factorizations, because they can really simplify problems from finding the value of a, which would be almost impossible, just applying a simple factorization. So this is the last problem for today. And this actually is a really nice solution. Okay, so we have a bunch of these terms, something to the power of 4 plus 324. So we have a bunch of these x to the 4 plus 324 terms. But something we might see here is that this is equal to x to the 4 plus 4 times 81, or x to the 4 plus 4 times 3 to the 4. That seems interesting. Does it seem familiar in any way? Any of the factorizations we learned in the class? Does this quantity seem familiar? It's just Sophie Germain's identity. So we can say that x to the 4 plus 4 times 3 to the 4. This will just be equal to, by Sophie Germain's, well, by Sophie Germain's we know that x to the 4 plus 4 times y to the 4 is equal to x squared minus 2xy plus 2y squared, x squared plus 2xy plus 2y squared. So then x to the 4 plus 4 times 3 to the 4 will just be equal to, we can substitute y equals 3 to get x squared minus 2x times 3 plus 2y squared times x squared plus 2x times 3 plus 2y squared. Oh, no, yeah, right. I don't know why I'm writing y. We know y is 3, so it's going to be 2 times 3 squared, so plus 2 times 3 squared. So here, not y is also correct, but we're substituting y to be 3 squared. So 2 times 3 squared. This is equal to x squared minus 6x plus 18 times x squared plus 6x plus 18. Because that's good for us. So now we can maybe factor our expressions here. So there's now from here 2 ways to proceed. One way, just to literally substitute x equals 10, x equals 4, and substitute a few terms here. And then you'll find that it actually telescopes. And if you remember from the AMC 8 telescoping class, telescoping just canceling, lots of canceling. So if we expanded each of these quantities, or even the first few and last few, we'll see that they cancel tremendously. So that's one way of doing it. But that problem with that way is it involves a lot of computation. And a lot of computation means a lot of ways to basically screw up in your solution and make a silly mistake. So there's a more clever way of approaching this that does not involve as much computation and opportunities to make a mistake. That clever way is, you can see that this is just x times x minus 6 plus 18 times x plus 6 times 18. So So this is a more clever way of approaching it. The reason is now that we can see that basically each x to the 4th plus 324 term can be expressed as a product of two terms, a larger one and a smaller one. So from here, we'll actually see, I'll explain it more later, but the smaller term of this expression will be equal to the larger term of this expression. So let me write that out just to make it more clear. So you can substitute x equals 10 to get 10 times 10 minus 6 plus 18 times 10 times 10 plus 6 plus 18. Oh, this is going to take a lot of space. I probably shouldn't write that many. Okay, so that's the first term. All the way to the right. This is going to take a lot of space to write, so I need to make sure I have as much room as possible. And then over in the denominator, I have 4 times 4 minus 6 plus 18 times 4 plus 6 plus 18. And then we multiply that by the second term. And then the second term is going to be equal to 22 times 22 minus 6. I'm plugging in 22 now. Plus 18 times 22 times 22 plus 6 plus 18. And then divided by 22 times 22 plus 6 plus, but it's going to be 28 denominator, so it's going to be 28 times 28. 8 plus 6 minus 6 plus 18 times 28 times 28 plus 6 plus 18. And this is just, we can continue writing more terms, or we can see that 10 times 10 minus 6 plus 18 is equal to 10 times 4 plus 18. Similarly, this is 4 times 10 plus 18. 4 times 10, it's 4 plus 6 is 10. And these are the same, so these terms will cancel. Similarly, this is 10 times 16 plus 18. And this bottom term is, or maybe I should have written it in a better way, but we can actually see that from here that this term, 4 times 10 plus 8, will cancel from this term here. And then we see that this bottom up term is 10 times 16 plus 18. And the term here, so as you can see here, the term will just be equal to, oh, sorry, this should be 16. Not 28. I got the number wrong, so it should be 16 actually. 16 times 16 minus 6. And 16 times 16 plus 6 plus 18. So this bottom term is going to be 16 times 10. Let me write a different color. 16 times 10 plus 18. This top term is 10 times 16 plus 18. So then we'll see that these terms cancel. And you can continue writing out more terms, and we'll see that they continue canceling out. Dot, dot, dot. All the way until the last term. And let me write out the last term. So I'm just breaking it down into 10 to the 4 divided by 4 to the 4 plus 324. 22 to the 4 plus 324 by 16 to the 4 plus 324. And the last term is 58 to the 4 plus 324. Or 52 to the 4 plus 324. So the last term can be written as we plug in 58 and plug in 52. This is just 58 times 52 plus 18 times 58 times 64 plus 18 divided by, so I don't want to get confused again, so 52 times 46 plus 18 times 52 times 58 plus 18. Okay, so now what? Well, now we see that these terms are equal. And I probably should have written it out just to be clear, but this is supposed to be 52 plus 6, or yeah, this should be 58 minus 6, this is 58 plus 6, this is 52 minus 6, and this is 52 plus 6. And these terms will cancel. And similarly, this term will also cancel with the term here, this term will cancel with the term here, and so on. And all these terms will cancel. And we're just going to be left with this term here, which is equal to 4 times negative 2 plus 18, which is 10. And this term on top here, which is just going to be equal to 58 times 64 plus 18, which is, well, a quick way of doing this is 61 squared minus 3 squared plus 18. And that should be equal to 3730. So now we have 3730 divided by 10, which should be 373, which is the answer to this problem. And yes, this was a tricky problem and a little bit bashy, but it had a really nice idea of applying Sophie Germains and recognizing Sophie Germains. So for factorization problems, knowing the factorization is just one part of it. Knowing when to apply it is the main tricky part of the problems. So again, be on the lookout for powers, exponents. Typically, think of factorizations when you're dealing with those kinds of things. And that's it for this video. If you enjoyed this video, be also sure to like and subscribe. And also leave a comment down below of which one of these problems was your favorite problem to do. Thanks for watching this video.